All right, I'm back again to continue. Hope all is well. To give you some incentive, I get it's kind of boring to listen to someone talk. It's much more, or it's much better if we could do this interactive. Maybe I'll look into that in the future. But at the very end of this, we'll sort of do some math humor for the day. So I'm going to recap what we did in the first part of that video. Formal definition of a limit. The epsilon delta definition. So if we can show that the absolute value of f at x minus L, that's what our limiting value is less than epsilon, whenever the absolute value of x minus a is less than delta. So we're going to have to show for every possible epsilon, we can pick a delta, start here on this side, and then show that that happens to be true. Now I'm just going to come over here for a second, just to show you in this case. Let me just get rid of that ink that's on there from my test earlier on. So notice now when I lower epsilon, I can zoom in here to find a delta, because when x is 2 over here, because a is 2 and 2 squared is 4, and that's where I'm at, this limit is indeed true. So as I lower epsilon, I am able to find a delta. But what happens now, let's put epsilon back up to a higher number now. Let's move this to something that's incorrect. So 9. 2 squared is not 9. Now watch what happens as I lower epsilon. I can't find a corresponding delta. We should be in this area because the corresponding deltas are around 3. So in this case, this limit isn't going to be true. And what we're going to work on today is formally proving limits. So I'm going to go to slide 17. And on slide 17, if we're going to prove a limit is true, what we're going to do is we're going to start with the absolute value of f at x minus L is less than epsilon, and then we're going to manipulate that side, and then we're going to try to express it in terms of the absolute value of x minus a. And then we'll use that to pick a delta. It might be possible that it comes into a factored form, and I've got the absolute value of x minus a, which is what I need, but then I got this extra piece, the absolute value of x minus d, and I'm going to have to find a bound for that. And to do that, we're going to allow delta to be equal to 1. But more on that later when we get to a specific example. So I'm going to explain this one, and then you're going to try the one on the next slide. So I'd like to show that the limit as x goes to 4 of 3x minus 1 is 11. I'm going to start with the absolute value of f at x, which is sitting right here, minus the limiting number, which is L, is less than epsilon. That becomes the absolute value of 3x minus 12 is less than epsilon. I can factor a 3 out, and that gives me 3 times the absolute value of x minus 4 is less than epsilon. And now, when I divide by 3, notice what we were able to create here. This is x minus a. So this was my scratch work in university. They'll tell you that. This is your scratch work. It is not the proof, because in the proof, we need to start with the delta. So right now, this is telling me I should choose delta to be epsilon over 3. So I'm going to start my proof on this bit over here now, using what I've determined from the scratch work, which told me what delta should be. So if delta is epsilon over 3, then we start with, I'm going to go just jump back to this slide so we can see again. I start from here. The absolute value of x minus a is less than delta. We also know that we're supposed to be choosing deltas greater than 0. So I put that part there, but it's not necessary for that to be there. The absolute value of x minus 4 is less than delta. We have that delta is epsilon over 3. So I now have the absolute value of x minus 4 is less than epsilon over 3. Cross multiply to get 3 times the absolute value of x minus 4 is less than epsilon. I can bring this inside of the absolute value because it's a positive number. And we would never choose delta to be negative anyways because we're not supposed to. It is larger than 0. And then when I pass this through and distribute, I get the absolute value of 3x minus 12 is less than epsilon, which I can break up into the absolute value of 3x minus 1 minus 11 is less than epsilon. So I was able to start from here and build to what we need. And again, quickly going back to slide 9, I started here and was able to demonstrate that that is true. Now you're going to try it on the next one and look where we started. We started with the absolute value of f at x minus L was less than epsilon, and then we used that to build an expression involving the absolute value of x minus a. So I'm going to move to this slide, and if you have printed the slide in front of you, I did change this to make this a little bit more challenging. So it's the limit as x goes to 3 of 2x minus 1 is 5. I'd like you to prove that that limit is true. You can start with some scratch work first. I'm going to suggest you pause the video now and you try this on your own. All right, so presuming you did some work on your own now, so what we're going to do is we're going to start with the absolute value. This is my scratch work. The absolute value of 2x minus 1, and then we're going to do minus 5 is less than epsilon. This gives us the absolute value of 2x minus 6 is less than epsilon. We can take a 2 out. We'll get 2 times the absolute value of x minus 3 is less than epsilon. And that's going to give us the absolute value of x minus 3 is less than epsilon over 2. So if we jump back to the previous slide, what have we done now? We've now found what delta should be. Delta should be epsilon over 2. So we're going to start our proof, and I'm going to change pen color. So this is not the proof, this is really our scratch work. Now in our proof, what we're going to do is we're going to choose delta equals epsilon over 2. And then we're going to end up having to start with this side now. So we're going to be looking at the absolute value of x minus 3 is less than delta. That gives us the absolute value of x minus 3 is less than epsilon over 2. Extend my page a bit. Cross multiply. 2 times the absolute value of x minus 3 is less than epsilon. I can bring that inside. The absolute value of 2 times x minus 3 is less than epsilon. Expanding, the absolute value of 2x minus 6 is less than epsilon. And one last manipulation to get it up to there. Now the absolute value of 2x minus 1 minus 5 is less than epsilon. And now I've been able to prove that if I choose my deltas to be epsilon over 2, every epsilon does indeed have a delta, and I can start from here and get down to there. So that's an example of working with a linear function. What happens if it's not linear? So let's take a look at this next example. In this next example, we're looking at a quadratic function. And I would like to show that the limit as x goes to negative 1 of x squared minus 3 is negative 2. Now, if we quickly substitute that in, you don't want to try and prove a limit's true if it's not. If we plug in negative 1, 1 minus 3 is negative 2. So I'm going to start with the absolute value of f at x. There it is. Minus L is negative 2. This simplifies to give me the absolute value of x squared minus 1 is less than epsilon. Now notice this factors, right, into the absolute value of x minus 1 times x plus 1. And this here is the piece we do need, because there's our x plus 1 from here, because we're trying to look at the absolute value of x minus our a value, which is negative 1 is less than delta. So this piece we need. However, we have a problem with this piece, because delta cannot be dependent on an x. So I now need to bound this. So how do I bound it? The bounds are always created the same way. They'll be created the same way in university. You're going to allow delta to be 1. And if delta is 1, the absolute value of x plus 1 is less than delta, I can now replace a delta with 1. This now means that x plus 1 needs to be between negative 1 and 1. That's a property of absolute value. And then what I'm going to do is build in the middle. I want this to become x minus 1, so I'll subtract 2 from all 3 pieces. That gives me negative 3 is less than x minus 1, which is less than negative 1. And now when I put absolute values around this, these will become positive, so I need to switch their positions, or I could turn the inequalities. I prefer to switch their positions. So 1 is less than the absolute value of x minus 1, which is less than 3. That now gives me this important constraint. The absolute value of x minus 1 is guaranteed to be less than 3 as long as delta is 1. I'm now going to come back over here, and I am going to replace the absolute value of x minus 1 with what did I type over here? The absolute value of x minus 1 is the one that's being replaced with 3 right there. The other thing I should note is the absolute value of, maybe I'll write this over here so we can see this. The absolute value of AB is going to be equal to the absolute value of A times the absolute value of B. Just want to make sure that we're aware of that. Those two will be equal to each other. So I can take these out of the absolute values. I'm now going to replace the absolute value of x minus 1 with 3, because I know it's guaranteed to be no larger than 3. And then I'm going to now isolate the absolute value of x plus 1, and I'm going to get the absolute value of x plus 1 is less than epsilon over 3. And then the trick we do is we now choose delta to be the minimum of 1 and epsilon over 3. And if delta is smaller than 1, then we know that this fact is true. So that's where this is coming from over here, because we are the smaller of them. So if it's 1, this is true. If it's smaller than 1, this is still true. And if we are smaller than epsilon over 3, then we can make this statement. And then what we're going to do is we're going to use the multiplicative properties of inequalities, which essentially says this. I'm going to write this over here as well. A is less than B, and we have C is less than D, then AC is less than BD. That's the multiplicative property of an inequality. So I'm now going to use that property. I'm going to multiply this by this, and that by that. This statement needs to be true. I can bring these back inside based on this property here, and I now have the absolute value of x plus 1 times x minus 1. That times that gives me my epsilon. I'm at the absolute value of x squared minus 1 is less than epsilon. And now I have I can break that apart into the absolute value of x squared minus 3 plus 2, which then can become the absolute value of x squared minus 3 take away negative 2, and then I've built back up to there. So again, this one has an extra step. You're going to have to allow delta to be 1 so you can find a bound for the other, I guess I'm going to call that binomial factor. So you're going to try that on this one. I'm going to suggest again that you stop the recording at this point in time. Initially set up like this, the absolute value of f at x minus your L is less than epsilon. That thing will be factorable. You're going to have two factors, one of which you need based on your A value. To find a bound for the other one, you're going to let delta be equal to 1.